Hello and welcome to an FPGA vision video. In this video we look at the VHDL design of a video generator for an FPGA implementation. And we start with the specification. We want to have a video generator for 720p format, so we need as an input the clock for this video signal of 74.25 MHz. We also want to have 3 switches to control the video signal, and we have a reset. The output of our circuit are the sync signals, the 3 sync signals, and the image data red, green, blue. And what we also have is a copy of the input clock that is helpful for takeover of the output signal. The code for this video generator is given on GitHub, so you can find it there for your own design. In VHDL, you start with the entity. So you need an entity for your module, which is called video generator. And basically it just gives the specification of the input signals and the output signals. So what you'll find here is basically the same information you had on the previous slide, the input signals and the output signals. And some of these signals are buses. So you have 3-bit input for the switches, and you have 8-bit output for RGB. Then we have to think about the block diagram. How do we want to design our circuit? And the design basically follows the concept of the row and column design of the video signal. So you have 2 counters, one counter for the row and a second counter for the column. And the counting cycle for these are according to the 720p video timing. If the row counter is at the end of its cycle, it increases the column counter. And with the position of row and column, you then go into if queries to generate the H-sync signal, the V-sync signal, and the data enable. And you also generate the RGB values. We make a simple example. I promised you to have a beginner example, so the graphics will be very easy, very simple, hopefully very well understandable for you. So this is the VHDL code for the row and column counter. If reset is 1, we reset everything. And then we have a horizontal counter where we increment the horizontal counter by 1 with every clock cycle. If we reach the end of the cycle, which is 1650 minus 1, so 1650 total pixel, this comes from the 720p format, we set the horizontal counter to 0 again, and we increment the vertical counter. If the vertical counter reaches 750, again, from the 720p format, we set it to 0 and start with a new frame. And we indicate this with this control signal. So we have 2 counters, where one counter controls the second counter. With the information from this counter, we can then generate the sync signals. So here we have the horizontal sync, and if the horizontal counter is smaller than 40, we set the horizontal sync to 1. This is the beginning of the line, otherwise it's 0. Same for the vertical counter. If the vertical counter is a smaller 5, we set vertical sync to 1, otherwise it's 0. And the values for these sync signals we get from the specification of the 720p format. You can search that in the web. There are specifications for the timing of the 720p format available on different websites. There might be variations. The version that I use here in my example and also on my GitHub page works with the frame grabber in our remote lab. With the same approach, we can now also generate data enable and red, green, blue. So we check if we are at the right position of the image, and this is a certain position for the horizontal counter and the vertical counter. This is the active image. If we are In this region we have the active image, so we set data enable to 1, and we set the image to gray, so red, green, blue we set to 128. Outside the active area we have no image, we set data enable to 0, and we set red, green, blue to black. So what we have now is an active image which is totally gray, so not very interesting. Therefore, we add further code. We add something. We add, in this case, a red square. We again check the position of our counter. If we are horizontally between 400 and 500 and vertically between 200 and 300, we set the pixels to red. So red is 255, green and blue is 0. And this overrides the red, green, blue we had earlier. So this is a property of VHDL. You can have multiple assignments to signals. First we set everything to gray, and then if this condition is met, we set it to red, and during design synthesis for the circuit, this will be converted to a circuit during synthesis. One note, if I write here about position 400, 500, this refers to the position including inactive area. This is not very intuitive, so you always have to consider that you don't have the position of the active image. This is something you could correct. To complete the VHDL code, we need the beginning of our architecture. This is given here. So we have the architecture and the signal definitions. Here is the process that is required for synchronous logic. We have here wait until rising edge from clock. So everything that comes behind this statement is synchronous logic. And what we do first here is that we have input flip-flops for all the signals. This is recommended to have proper timing. Likewise, at the end of the code, we also have output flip-flops. So we give now the signals that we had internally in our architecture to the output, again with the flip-flop, because it's inside the process. And then we end the process. Here we also have the clock output, and then we have end behave. This is the end of the architecture. A small extension to the VHDL code, we have here a second square that we want to have on our VHDL code. This is a green square, and we want to make this one moving. So yeah, a bit more complex. If you understood the red square, fine. This is just one modification to it. So we now have here some VHDL code to have a starting and end position. So we have starting position of 600 and position of 700. And with each frame, if new frame is 1, we increment these positions by 1 until start position reaches 800, when we go back to 600. It's important here to use this new frame control signal. If we don't do this, we would increment the position for every clock cycle. So this would be 1650 times, 750 times per frame. This is not what we want. We want to have it increment only once per frame. And then with this H start and H end, we can again have an if statement and check if our H counter and V counter is in this range. And if it's in the range, we set the pixel to green. So now we have a video generator for 720p signals with a gray background and 2 squares, where 1 square is moving. In the next video, we look at VHDL simulation for verification of this design.